Dark Energy Explained, Unraveling the Universe's Greatest Mystery. For centuries, we thought we had the universe figured out. The Big Bang happened, and ever since, the universe has been expanding, right? And logic told us that gravity, the ultimate cosmic glue, should be slowing that expansion down. But then, in 1998, something truly mind-blowing happened. Two independent teams of astronomers looked out into the cosmos and discovered something completely unexpected. The universe isn't slowing down. It's speeding up. This wasn't just a small tweak to our understanding. It was a cosmic bombshell. What force could possibly be pushing everything apart faster and faster? That is the mystery of dark energy. So what is this mysterious force? Scientists call it dark energy. It's a placeholder name, really, because we still don't know its true nature. We can't see it, we can't touch it, and we certainly can't measure it directly. But here's the kicker. This invisible force isn't some minor player. It's believed to make up a staggering 68 to 70% of the entire universe's mass energy density, making it the most dominant constituent. To better understand it, it is crucial to distinguish dark energy from dark matter. Dark matter is an invisible substance that clumps around galaxies and exerts gravitational attraction, helping structures form and holding galaxies together. Dark energy, in contrast, appears to be uniformly distributed across the universe and exerts a repulsive anti-gravitational force, pushing galaxies apart. This distinction sets up a fundamental cosmic tug-of-war. On one hand, dark matter is attempting to pull things together, fostering structure formation. On the other, dark energy is actively pushing them apart. This dynamic tension dictates the evolution of the universe's large-scale structure. It implies that the universe's destiny is not solely determined by the attractive force of matter, but by the interplay of attraction and this mysterious repulsion, leading to complex and potentially dramatic future scenarios. And right now, dark energy is winning. So, how did we even find something we can't see? It wasn't a direct observation. It was a cosmic detective story using something called Type 1a supernovae as our clues. Imagine these supernovae as cosmic standard candles. They're exploding white dwarf stars that always reach the same peak brightness, like a perfectly calibrated light bulb in the sky. By measuring how bright these supernovae appeared from Earth, scientists could determine their distance. The dimmer they look, the further away they are. They then compared this distance to how much the universe had expanded since the supernova exploded, using something called redshift. Here's where it gets wild. The distant supernovae were dimmer than expected, much dimmer. This meant they were much further away than they should have been if the universe was just slowing down. The only way for them to be that far was if the universe's expansion had been accelerating, pushing them away even faster over time. This unexpected dimness was the smoking gun, the first real evidence that dark energy was out there, silently shaping our universe. But the supernovae weren't the only clue. The universe has left us other breadcrumbs. One of the most powerful comes from the cosmic microwave background, or CMB. This is the faint echo of the Big Bang itself, a relic radiation that fills the entire universe. By studying its tiny temperature fluctuations, scientists can deduce the total energy density of the universe. And you know what? The CMB tells us our universe is flat, which means it needs a specific amount of total energy. Regular matter and dark matter just don't add up to that amount. The missing piece? You guessed it, dark energy, making up the difference. Then there's the large-scale structure of the universe, the cosmic web of galaxies, filaments, and vast empty voids. Gravity tries to pull these structures together, but dark energy's repulsive force slows that process down. By mapping how this cosmic web has grown over billions of years, we get more insights into dark energy's influence. Even the subtle bending of light from distant galaxies due to gravitational lensing also gives us hints, as dark energy subtly alters the path of light. All these independent observations, from baryon acoustic oscillations to galaxy clusters and even new techniques using gravitational waves, point to the same conclusion. Dark energy is real, and it's driving the universe's acceleration. So what could dark energy be? Scientists have a few leading ideas. The most popular and simplest is the cosmological constant, or lambda. This theory suggests dark energy is just the inherent energy of empty space itself, vacuum energy. It's constant, uniform, and doesn't change as the universe expands. Fun fact, Einstein actually introduced a similar concept, his cosmological constant, to keep the universe static in his equations, a move he later regretted. But here's the problem. When quantum theory tries to calculate this vacuum energy, the numbers are off by a mind-boggling 100 orders of magnitude. This cosmological constant problem is one of physics's biggest headaches. Then there's quintessence. This theory proposes dark energy isn't constant, but a dynamic, evolving energy field, kind of like a cosmic magnetic field. Its properties could change over time. And get this, recent surveys, like those from the DESI instrument, have found hints that dark energy might actually be weakening. If true, this would be a game changer, challenging the constant model and completely reshaping our cosmic future. Finally, there's the radical idea of modified gravity. What if Einstein's general relativity, our bedrock theory of gravity, isn't quite right on cosmic scales? Maybe we don't need a new energy source. Maybe gravity itself behaves differently at vast distances. While general relativity has passed every test so far, dark energy forces us to consider even our most fundamental laws. The ultimate question: what does dark energy mean for the fate of our universe? Its properties will decide everything. If dark energy remains constant and dominant, the universe will continue to expand at an ever-increasing rate forever. Galaxies not already gravitationally bound will fly further and further apart, eventually becoming isolated, with the night sky growing increasingly dark and empty. This chilling scenario is often referred to as the Big Freeze or heat death. Conversely, if dark energy were to strengthen over time, a possibility within some quintessence models, its repulsive force could become so powerful that it would eventually overcome all other forces, tearing apart galaxies, stars, planets, and even atoms themselves. This catastrophic scenario is known as the Big Rip. On the other hand, if dark energy were to weaken significantly or even reverse its repulsive nature, gravity could eventually regain dominance, causing the universe's expansion to halt and then reverse, leading to a collapse back into an incredibly hot, dense state, similar to the Big Bang in reverse. This is the Big Crunch scenario. Currently, the continued accelerated expansion scenario is the most widely accepted. However, the evolving nature of dark energy could change this picture. New results from the Dark Energy Spectroscopic Instrument, DESI, suggest dark energy may be changing over time. This highlights the dynamic interplay between theoretical models and observational data in cosmology, where new data can rapidly shift our understanding of the universe's ultimate end. The uncertainty about dark energy's evolution means the universe's fate is still an open question, driving current research. So, despite all we've learned, dark energy remains one of the biggest unsolved puzzles in physics. What is it really? Is it constant, or does it change? And how does it fit into the grand scheme of fundamental forces? One of the most intriguing clues right now is the Hubble Tension, a baffling disagreement between different measurements of the universe's expansion rate. It's like two highly accurate rulers giving different answers for the same distance. This isn't just a measurement error. It suggests our standard model of cosmology might be incomplete, or that there's new, unknown physics at play, perhaps involving dark energy, dark matter, or even neutrinos. Solving this tension could unlock secrets not just about dark energy, but about the entire dark sector of our universe. Large-scale surveys like the Dark Energy Survey and the Dark Energy Spectroscopic Instrument are working tirelessly, mapping billions of galaxies to gather more data and finally pin down the true nature of this cosmic enigma. Dark energy is a profound reminder of how much is still to be learned about the cosmos. It challenges our most fundamental theories and pushes the boundaries of human knowledge. The quest to understand dark energy is a vibrant frontier of scientific discovery, promising to reshape our understanding of the universe's past, present, and ultimate future. What do you think dark energy is? Let us know in the comments below. If you enjoyed this cosmic journey, hit that like button, subscribe to Cosmic Enigma for more mind-bending science, and ring the notification bell so you don't miss our next exploration. Until next time, keep looking up.